Hello and welcome to this series of videos on algorithms and data structures. The first video we will be talking about time complexity and algorithms. To understand algorithms, we first need to talk about the big elephant in the room, the big O notation. The big O, or asymptotical notation, is a mathematical notation that describes the limiting behavior of a function, which means how a function or algorithm behave when a variable tends to infinity. We use this to classify algorithms depending on how their space or runtime grows with the increase of its input size. Related to big O, we have other notations such as small o, big omega, and theta. The difference between big and small o is basically that big O is inclusive, which means that they can have the same value at certain points, and the small one is a strict upper bound. But what are all of these letters? Let me tell you with a story. In a faraway land, there's a princess called Olga. She has a flying unicorn that she loves to ride. But her mother is worried to leave her fly alone, so she asks the court to take care of her. These are the knights that will take care of her. They have a specific flying formation. Big O is always flying above the princess, and she makes sure that the princess doesn't fly too high. Omega flies under the princess, making sure she doesn't fall. And Theta flies at the exact same altitude as the princess. In the end, the most important notation is big O, as it's the upper bound and the one we will see our results getting closer to in the worst case scenario. As an example, we can take this function and draw its graph. This will be its big O notation, but when it gets high enough, we can just simplify it as big O of n, as the other numbers won't influence it too much. Some of the most common big O cases are constants, for example, getting an item with an index in an array; logarithmic, finding an item in a sorted array via binary search; linear, doing linear search in an unsorted array; quadratic, such as the worst case scenario of bubble sort; and, in the worst cases, exponentials and factorials. Now that we have the classificatory notation, let's have examples with some popular algorithms, like the binary search for sorted arrays. The binary search takes an item, hopefully near the middle of the array, and checks if it's the one we are searching for. If it's not, it then checks if it's a smaller or bigger. Let's say that it's bigger. It proceeds to create a new array with only the items right of the one we compared before. And it repeats these two loops until finding the right item. This has a logarithmic complexity, as we can see here. But that takes a sorted array, so how can we sort one that is unsorted? We can use other algorithms, like quicksort. Quicksort has its name for being faster, if well implemented, than merge sort or heap sort. And it's a divide and conquer algorithm. It takes an item, hopefully the median of the array, that we will call a pivot, and compares it to all the other items, shifting them around until it has all the lower occurrences to the left and the greater ones to the right. Then it makes subarrays around it and does the same process in these smaller arrays. Then it joins it at the end to have a complete sorted array. It has a logarithmic complexity if the pivot is chosen well. And that's a very quick overview of algorithms and time complexities.